This is chapter 3 of Matter and Energy. Section 3 is all about energy. Energy is a way that we can quantify the relationships between objects. And broadly speaking, it breaks down into two different kinds. So we have the relationship between objects in terms of their relative position, and this can be quantified as their potential energy. Or we have the relationship in terms of their movement or their motion relative to one another, and this can be quantified as their kinetic energy. Again, kinetic energy is the energy an object has because of its motion. Some examples of some things that have kinetic energy are a person swimming, the water flowing over a dam in this picture here, or an arrow flying through the air. So anything that's moving has kinetic energy. And here we see the movement of the water over this dam as it flows from this region up here over and down. As it falls down, it is gaining kinetic energy. Potential energy is the energy an object has due to its position relative to other objects. So, for example, the water at the top of the dam on the previous slide has a certain potential energy relative to the surface of the Earth. And when the dam is opened, the water flows through and that potential energy is converted into kinetic energy. A compressed spring is an example of potential energy. If you take a spring and you compress it down and you hold it so that it's compressed, it's not moving, but it is containing energy. It's containing energy in the arrangement of the material, the matter that makes up the spring. And if you were to let it go, that potential energy would be converted into the kinetic energy of the spring bouncing back. And then the last kind of potential energy, or the last example, is chemical bonds. Okay? Chemical bonds are really descriptions of relationships between the arrangements of atoms in a compound. So some examples of substances that contain a lot of potential energy in the form of chemical bonds are gasoline, coal, and food, right? Gasoline and coal, we understand, are fuels that we use, right? Gasoline is burned in your car, and the potential energy or the chemical energy in the gasoline is converted into the kinetic energy of your car moving. Food is the same, though. The food that we eat provides all of our energy that we need to live and to breathe, okay? And it's all stored in the chemical bonds of the food. We break the food down through digestion and process it and extract energy from it. So for each of these systems, we want to identify whether they are an example of potential or kinetic energy. So for instance, the first one is rollerblading. Rollerblading is obviously movement or motion, so that's a good example of kinetic energy. A peanut butter and jelly sandwich obviously is a type of food, and so it contains energy in its composition and the chemical bonds within it. So that is potential energy. Mowing the lawn is again a motion, it's an activity where you move, and so that is kinetic energy. Gasoline in the gas tank, we saw already, that is an example of potential energy. Now, one thing to keep in mind is that even though these are the answers that we're expecting here, and we think of these things as representing either kinetic or potential energy better, virtually every system in the universe is some combination of both kinetic and potential energy. So a person rollerblading has kinetic energy because they're moving, but they also have some potential energy relative to the center of the Earth, say. A peanut butter and jelly sandwich we think of as being potential energy or having potential energy, but it also has a lot of kinetic energy because at a microscopic level, all of the molecules in the peanut butter and jelly sandwich are all vibrating and moving around quite a bit. So it also has kinetic energy. Mowing the lawn, same as rollerblading, right? It's movement, but we can also consider it to have potential energy relative to the Earth. And gasoline, just like the peanut butter and jelly sandwich, is potential energy, but it also has movement in the molecular motion. Okay, so that's a form of kinetic energy. So everything is a combination. And so when we ask a question like this, or we think about a system like this, we're really thinking about or asking what is the most noticeable form of energy that this system represents. So if we think about how the peanut butter and jelly sandwich or the gasoline from the previous slide actually have kinetic energy in terms of the motion of the molecules within them, then we can start to understand that heat is actually a kind of disordered kinetic energy. So heat is the energy associated with that microscopic motion. right? It's a random, it's in all directions, it's disordered. So heat energy does not move you in any one direction on a macroscopic scale, but it is a lot of motion on the microscopic scale. The faster that the particles in a substance move, the more kinetic energy they have, and the greater the heat or thermal energy of the substance is. So, for example, if you have an ice cube, well, the ice cube consists of water molecules that have very little energy. They're packed close together and they have fixed positions relative to one another, right? That's characteristic of a solid, as we learned in previous slides. So as you heat the ice up, though, you give those molecules more and more energy. And the first thing that happens is that they start to vibrate a little bit more, they start to move a little bit more, and then eventually they get enough energy that they can break away from their fixed positions. Okay? They're still going to be close together at this point, but they're not going to be static relative to one another, and they'll begin to move past one another. And once all of the particles, all of the molecules in a piece of ice have enough energy that they can break away from their fixed position and move relative to one another, then that ice has melted into a liquid. Okay, so the liquid has more energy on average per particle than the ice does. The units of energy are the joule in the SI system, and the joule can be expanded using the same metric prefixes. So you can talk about kilojoules or millijoules or megajoules or whatever other prefix you want to add in front. In chemistry, however, we more frequently use the calorie unit or even the kilocalorie unit. 1,000 calories are in a kilocalorie. So the joule is usually more for physics type settings or contexts, whereas in chemistry we talk about calories. And we'll see later on in these slides how this calorie is related to what we think of as calories in our diet. They're not exactly the same, but they are very closely related. So there is a relationship between these two things, right? These are both units to measure energy, and so therefore there must be some corresponding relationship between them. And the relationship is this: 1 calorie equals 4.184 joules. This is considered to be an exact number. In other words, the calorie and the joules have been defined relative to one another. So even though they're not the exact same system or the exact same measurement, this is considered an exact relationship. And we can define two conversion factors as a consequence of this. And so we can convert between calories and joules. One other thing to note is that the definition of a calorie is that it's the amount of energy that we need to raise the temperature of 1 gram of water by 1 degree Celsius. And we'll see more about that. We'll talk about that more in detail when we deal with specific heat later on. Here we see a scale comparing the energies contained in different natural systems. So for example, at the very bottom here, we have the energy that we use to sleep for an hour. So even if you're asleep, you're not moving too much, although you may toss and turn, that requires some energy, but you're also dreaming, your brain is still working, your metabolism is still functioning, right? You're still breathing. All these things require energy. And so even when you're asleep, you use up about 10 to the 5th joules of energy per hour. That's 100,000 joules or 100 kilojoules per hour. If you are bicycling for an hour, you use 10 times as much, or 1,000,000 joules per hour. And this is approximately the same amount of energy that you would get from 1 serving of pasta or from a donut. And then we can see even higher than that is the energy that can be obtained from a gallon of gasoline. So a gallon of gasoline has 10 to the 8th joules of energy. So that is 100 million joules of energy. So it's 100 times more. So you can see that gasoline has a much higher energy density than the energy in our food, like a donut or in pasta. And so that's why your car runs on gasoline rather than donuts. It's much more efficient that way. And then we get to larger things where we're talking about like the collective energy. Well, this is energy used per person throughout a whole year in the United States, 10 to the 11th. So this is 1,000 times larger than the energy from a gallon of gasoline. And then even larger than that is the solar energy reaching the Earth, 10 to the 17th. In 1 second, 10 to the 17th joules of energy reaches the Earth. So that is 1,000,000 times larger. 10 to the 17th is 1,000,000 times larger than the amount of energy used per person per year in the United States. Enough solar energy reaches the Earth in 1 second to essentially last 1 million people a year in the United States. It's quite a bit. Then we have the total energy consumption, because there are a lot of people in the United States. The total energy consumption in 1 year is 10 to the 20th. And so that's bigger. It's 1,000 times larger than the solar energy per second, right? And then the world reserves of fossil fuel, 10 to the 23rd. So 1,000 times larger than this number. 1,000 times the energy consumption for the United States for 1 year. So if we, in the United States, we're the only ones using energy from fossil fuels and we burn through it at our current rate, it would be used up in 1,000 years. And then the energy radiated by the sun in total in 1 second is 10 to the 26th, though even 1,000 times larger than that. Now this is being radiated from the sun in all directions, so most of it, the vast majority of it, doesn't ever hit the Earth. It goes into the outer space outside of the solar system, but there's still vast amounts of energy. This is a straightforward question dealing with these new energy units that we learned about. It says, how many calories are obtained from a pat of butter if it provides 150 joules of energy when metabolized? So our initial measurement is going from 150 joules, and we're looking to convert that into how many calories that represents. So it's a simple, straightforward joule to calorie conversion. So, like with any conversion factor problem or any conversion problem, we start with the measurement that we're given, 150 joules, right? 150 joules right there in the problem, and we need to get calories from it. So what that means is we're going to need the energy factor, the conversion factor, to convert from joules to calories. That's not a conversion factor that you need to memorize. You will be given that for any questions that require you to do that sort of conversion. So our plan is very simple at this point, right? Write a plan to convert the given unit to the needed unit. Well, we're going to go straight from joules to calories in a one-step conversion using that single conversion factor. So let's see how that works. The conversion factor is that 1 calorie equals 4.184 joules. So we can use either this conversion factor or this conversion factor. Well, I should say we have to use one of them, not the other. So the question is going to be, which do we use? And again, we do that by working out the units. Here we can see that we begin with units of joules. Our initial measurement is 150 joules of energy. And so when we have this conversion factor, we put joules in the denominator. And that way we can cancel out this initial joules unit here. And that's going to leave us with this unit, calories, which we put on top, because calories is the unit that we want. So once we have the units in the correct place, then we can just fill in the correct conversion factor. 1 calorie equals 4.184 joules. So we take 150 joules and we multiply it by 1 over 4.184. That's the same thing as 150 divided by 4.184. And so the answer to 2 significant figures is 36 calories. The reason this is the only 2 significant figures is because our 150 has 2 significant figures. Okay, so the 1 is significant, the 5 is significant. Because it's not a decimal number, we can ignore this 0, and it is not a significant figure. So we have 2 significant figures in this measurement, and then we saw in the previous slide that the calorie to joule conversion is just considered to be exact. So both of these numbers, even though they're decimals, are considered exact numbers. So the only thing we're limited by are the significant figures of the 150 joules. And so we get 2 significant figures at the end.